So we are looking at shortest path problems on weighted graphs, and we started with the single source shortest path problem, and we looked at Dijkstra's algorithm, which works whenever there are no negative edge weights. So what happens if you do have negative edge weights? So let's look at the single source shortest path problem where there are negative weights. So let's revisit the proof of Dijkstra's algorithm and see what the problem is. Right? So we had this burning pipeline, and what we said was that we will keep track of the burnt vertices and how long it is going to take for the remaining vertices to burn, the expected burn time. So initially no vertex is burnt, and initially all vertices have an initial burn time of infinity, and then you burn one vertex. So the source vertex now acquires a burn time of 0. Right? And after this, what we do is we pick the unburnt vertex which has the smallest burn time or the smallest distance among the unvisited vertices. We burn it, we make its status change from unburnt to burnt or from unvisited to visited, and then we update, right? We update the time or the distance to all the neighbors. For every j, every k which is a neighbor of the vertex j that we just chose, we update its burning time to be the minimum of its already known burning time, or the burning time of j plus the distance from j to k. So for this to work, we had this proof which said basically that if I extend my thing in this direction, then coming from here cannot produce a shorter path, and this required all my edge weights to be non-negative, because we said for instance that if we had a negative weight like 5, 7 and minus 3, then we could in fact discover later on through W a shorter path in terms of the costs to V than we can discover right now. Right? So we could not apply this anymore. And one of the reasons that this happens is because we are kind of freezing this choice, right? So we are saying this is the shortest path we have discovered to V, and we have frozen it. Once we move it into this red part, the burnt vertices or the visited vertices, we are never going to update its thing again, right? So this is a kind of one-shot operation. I discover something is the current shortest, I make a decision to burn it or to visit it, and I will never reconsider that distance again. So even if I am presented with different information, I will not reconsider it. So if we have non-negative edge weights, I am guaranteed that I am not going to get contradictory information later on, so it is fine. So the obvious solution is to say, well, maybe if I find a later path which is better, maybe I allow myself to change it. Now the problem with this strategy is how many times will I do this? I mean, what will happen if I keep, setting it, changing it, setting it, changing it? How do I guarantee that this doesn't keep going on forever? So we are going to allow negative edge weights because that's the only scenario in which Dijkstra's algorithm will no longer work in the way that we said before. But remember that we don't allow negative cycles, right? So if we don't allow negative cycles, then we cannot have arbitrarily small path lengths. So if we go around a cycle, we cannot reduce the overall length of the path, right? So this means that there is no advantage to going around a cycle, right? If I go around a cycle, either I incur 0 cost, which is fine, or I incur some positive cost. So if I go around it, I might as well not go around it. So with this justification, we can easily argue that if I don't have negative cycles, then actually the shortest way to go from anywhere to anywhere must be a path, in the sense that we discussed before. A path is a sequence of edges which are connected to each other, which do not repeat a vertex. Right? A cycle is a situation where you will repeat a vertex, but going around a cycle has no advantage. So either it has 0 disadvantage, in which case you can still drop it because it only has cost 0, or it could have a real disadvantage because it has a positive weight, but it can never have a negative weight and give you a bonus. So with this in mind, okay, now we have some idea that among all the, so remember this single source path, right? So I am starting from S and I am trying to go to some T, and I might have many different ways of going from S to T, right? And I want the minimum among all these. But what I am guaranteed is that the shortest route from S to T is going to be a path. So it cannot pass through more than n minus 1 edges, because if it passes through n edges, then it will have to repeat a vertex and then it will no longer be a path. So there is an upper bound in terms of number of edges which are seen going from S to T, and this will help us to derive an algorithm for the case where we have negative edge weights. So supposing 0 is our starting vertex and we want to get to vertex k, and the shortest path follows these L edges, right. So, I have W1 to J1, then W2 to J2 and so on, and finally WL minus 1 to JL minus 1 and WL to K, right. So, I follow L edges. So, this, as we discussed, need not be the shortest in terms of number of edges, but the shortest in terms of number of weights. If I add up W1 plus W2 up to WL, I can find no shorter path. So, the first observation is that each of the paths before it must be themselves shorter, right. So, supposing for instance I could find a better path from 0 to J2, right. So, supposing there is something which with weight W prime which is less than W1 plus W2. Well, then I know that from J2 I can get to K, so I could choose the shorter path W prime and get a shorter path from 0 to K, which contradicts my assumption that 0 to K as stated is the shortest path. Right. So, therefore, if this is the shortest path, then 0 to JL minus 1 is also a shortest path, 0 to JL minus 2 is also a shortest path and so on. So, every one of the paths on the way to this K is also a shortest path up to that intermediate vertex. So, that means that if I can find shortest paths of length L minus 1, and if I know that K has a shortest path of length L, then for every vertex if I know the L minus 1 path of shortest length to that vertex, then among those I will get the shortest path of length L to K, right. So, this is the idea now, that we will keep updating the shortest path, and each time we update the shortest path, we would have discovered shortest paths up to a longer length. So, initially when we update shortest paths, we will only know shortest paths of length 1, path length 1, right. So, that is, if you remember our original picture, right. So, we had this 0, 1, 2 and we had these weights 10, 6 and 80. So, if I look at path length 1 starting from here, then I have basically this edge and this edge, right. So, this gives me this estimate of 80 and 10. Now, if I look at path lengths 2, right, so this is 80 and this is 10. If I look at path lengths 2, then this 80 becomes 16. So, the fact that there is a shortest path of length 2 to vertex 2 gets discovered after I find the shortest paths of length 1. So, in general, if I have a shortest path of length L, this will be discovered after I find the shortest paths of length L minus 1, and that is what we are going to do by iteratively updating. So, we are not going to freeze the update, but we are going to keep updating. Every time we make a change, we will update all the neighbors of that changed vertex, right. So, after L updates, the claim is that all the shortest paths using at most L edges would have reached their optimum. And since, as we discussed before, the shortest path to any vertex must be a path and it can have at most n minus 1 edges, if we do this n minus 1 times, we would have stabilized all the paths. Okay. So, this actually turns out to be a much simpler algorithm than Dijkstra's algorithm in some sense to implement. You first set the source vertex to be, let us assume the source vertex is 0, right. So, initially you assume the distance to 0 is 0 and for everything else is infinity. And now, every time you find a minimum vertex, right. So, for each edge, for every vertex, you know its estimate, you look at its outgoing edges and you re-establish the minimum for the outgoing thing. So, supposing I am currently at J and I have some outgoing things and I have some W1, W2, W3 as my estimates there, and I know my W here. So, I have D1, D2 and D3. So, at every point I will compare W1 with W plus D3, D1. I will compare W2 with W plus D2, right. So, I will update everything and I will update all its neighbors and I will keep doing this again and again, right. So, that is the algorithm. So, this works for both directed and undirected graphs. So, here is the algorithm. We will come back and look at it a little more carefully after we do a kind of run through of it. So, what we do is we take an adjacency matrix and a source vertex, right. As before, we figure out how many rows we have and we set this infinity in terms of the number of rows and the maximum value in the matrix. And now we have this distance dictionary which will give us a distance to everything. So, initialize all the distances to infinity and then set the distance of the source vertex to 0, right. And now we are going to do something n times, right? Actually n minus 1 times suffices, but we will do it n times. So, n times what do we do? For every vertex, for every v, so basically for every u, for every v, if uv is an edge, right, then we update the distance of v to be the minimum of the existing distance plus the distance of the starting point of the edge and the weight of the edge, right. So, we say d of v is going to be min of the existing distance plus or du plus the weight of this edge, and we just keep doing this blindly. And our analysis basically says if there are no negative cycles, then this is going to settle down, right. So, this is as you can see in terms of code, this is just a bunch of nested loops, and it's significantly simpler than Dijkstra's algorithm to implement. So, here is an example of a graph which has negative weight. So, you have these -4 and -1 and so on, but there are no negative cycles. So, for instance, if you go around this, there is a cycle, right, but along this path, this cycle you have -2 plus 1 plus 2. So, the total of this cycle is +1, right. So, in the same way you can look at other cycles. So, there is a cycle here, for instance, right, 6 to 1, 1 to 5, no, that is not a cycle, sorry. You have a cycle here, for instance, 5 to 2, 2 to 3, 3 to 4, and okay. So, here this -1, -2, +1, +3, -1, right. So, this again has a net of +1 because this -3 plus 4. So, in this graph we have negative edges, but no negative cycles, and in principle if I take 0 as my canonical starting vertex, right, this algorithm that we just discovered, we call the Bellman-Ford algorithm after two gentlemen, Bellman and Ford, right, this algorithm should actually produce the shortest paths from 0 to every other vertex. So, the way it works is we will keep this stage wise thing, right. So, initially we want at the 0th stage the distance to 0 is 0 and the distance to everything else is infinity, right, that is our initialization. Now, what I do is I take everything that is known and I update things which are unknown. So, what do I know? 0. So, if I know that 0 is 0, then this must be 8, and if I know 0 is 0, this must be 10. For everything else, my current estimate is infinity. So, infinity plus whatever is going to be infinity. So, basically I get a new distance for 7 and 1. So, vertex 1 is going to be 10 and vertex 7 is going to be 8, right. So, this is what I get. So, I get new entries here 7 and 8. Now, from this I can get that the distance to 6, okay. So, now I know something about 7, I know something about 0, I know something about 1. So, now I can update to 6, for example, from 7, I can update from 1 to 5, right, and so I get two new entries for 6 and 5, right. So, I keep doing this. So, now that I know all these things, I can update once more and I will get now information about 2. I get information about 2 because I know 5. So, I know from 5 to 2. So, 5 was at distance 12 before, and 12 minus 2 is going to be 2, right. So, I keep doing this and I do this blindly, and after the 7th iteration of this I stabilize, and this is going to be the shortest path from 0 to everything else. Okay. So, this is the Bellman-Ford algorithm. Now, if there was a negative cycle, then what would happen is that if I computed one more column of this, right, then I would find a longer path which has gone around the cycle, and then something will reduce one more time. So, this Bellman-Ford algorithm will work correctly if there is no negative cycles, but if there are negative edge weights. But also if I run it one more time, then it should stabilize, and it has not stabilized. So, I run it an 8th time for 7, rather a 9th time for these 8 vertices, and if it does not stabilize, that means actually there is something wrong. So, I can also detect negative cycles using Bellman-Ford, right. So, I just check if the nth update will reduce the distance to any vertex. If it does, then there is some negative cycle. So, here is the adjacency matrix version of it that we saw before, right. So, this is going to take now n squared time, right, and then this loop runs n times, right, and inside this loop we have this which is another n squared time, right? And so this whole thing is going to take, it should be n cubed, I think. Right? So this should take n cubed time. Right? So if we take adjacency lists instead, again this is an order m algorithm, right? And now this particular update inside, which was earlier taking n squared time, so remember this is n cubed, right? This earlier thing which was taking n squared time is now going to take order m time, right? I am going to take and update the distance across all the edges in my graph. I am not going to look at anything except an edge. So across all the vertices, I am going to look at all the neighbors, and that is going to be the sum of all the edges in my graph. So I will do that update, and that will be order m. Right? So therefore, I have an outer loop which is n, and inside that outer loop of n, I am doing order m operations. So I am going to do m times n. So remember that m is at most n squared, right? So m times n could be n cubed. But if m is small, for example, as we said, if m is linear in the number of vertices, then m times n could be n squared. So it could be one order of magnitude smaller than n cubed. So again, adjacency lists give us a much better complexity than adjacency matrices for Bellman-Ford, right? So Bellman-Ford allows us to do single source shortest path even in the presence of negative weights. So the point of Dijkstra's algorithm was that because of this assumption about non-negative weights, you could do this greedy update. Whenever you see the minimum distance to an unburnt vertex or unvisited vertex, you could freeze that and say forever this is the minimum distance. But if you have negative edges, you could later discover a shorter path to that vertex, and you have no way to update it in Dijkstra's algorithm. So what Bellman-Ford says is, well, you just go ahead and do it, right? You just, every time you see an update to a vertex, you update all its neighbors if they can be updated. And you are guaranteed, if there are no negative cycles, that this process of updating will stabilize after n minus 1 rounds. So after k rounds, it will stabilize all paths of length k. So after n minus 1 rounds, you will have all paths of length n minus 1, which will cover all the shortest paths. So by repeatedly doing this blind update in some sense, you uncover all shortest paths in the presence of negative edges. Right? So this takes n cubed time if you use an adjacency matrix, but if you use an adjacency list, is m times n, which in the worst case could be n cubed, but it could be much better if m is small. Right? And we can also exploit the fact that Bellman-Ford should converge, but if it does not converge, it tells us something interesting, which is that the distances continue to reduce, and therefore my assumption that there were no negative cycles is false. There are actually negative cycles in the graph. So by running Bellman-Ford one more time and checking if things change again, they can only change by going down, of course. If they go down, then it means that you have a negative cycle in your graph, and therefore this was not a valid graph to compute shortest paths at all.